Okay, hello, welcome to my tutorial about timing and synchronization. With the recent growth of fast LTE and appearance of 5G networks, there is more and more requirements on timing in packet networks. So this session is basically an introduction that will introduce the basics of different time synchronization methods in Ethernet networks. Let's start with the word from sponsors and quickly move to the agenda. So this session starts with basic definitions and background of timesync. The first chapter will actually define what can we synchronize in our systems and why actually do we need to. Then it will go over the basics of frequency synchronization done on different levels. So the first chapter will talk about the packet-based time and phase distribution. So we will talk about a little bit about the 1588 protocol. And then we will move on to the physical layer distribution. So we will introduce the Sinki. We will talk briefly about the ESMC messaging that is used along with Sinki to actually tell more about the classes of the clock and quality of the signals. And then we will talk about the frequency synchronization states, because in Sinki there are a couple different states. And after this, we will talk briefly about the traceability. So how can we actually trace different clock classes and what clocks are we using in our system? And we will end up with a short summary. So without further ado, let's move on to the first chapter. So what is actually clock? So there are the two main definitions inside the Wikipedia. So one of them is an instrument for measuring and showing time in a room, wall, building, or a computer screen, not worn or carried like a watch. And the other one is a clock signal. So this is a signal generated by oscillator that changes between high and low and is used as a hard digital circuit. So obviously, we will focus on the let me get the pointer on the clock signals throughout this discussion. We will actually the time whenever I will refer to the clock, this will be the physical signal. So what are the three things to synchronize? First one is frequency. So we need to make sure that, for example, 10 hertz or 10 megahertz is the same 10 hertz on all our devices in our system. And it's, and this means that we will get exactly 10 cycles in a second and not 9 or 11. Next one is phase synchronization. So we want to additionally make sure that the edges of our two clock signals starts at the same time. And the last thing to synchronize is time of day. So we want to know what day of week it is and don't miss the 5 p.m. on Friday. So the first thing we will talk about is the frequency synchronization. Technical term for frequency synchronization is synchronization. And well, imagine that basically what it means is that the events in our system will happen at the same rate. So you can imagine the process of, for example, one person washing dishes and the other trying them out. So if one person works faster than another, the dishes will pile up and finally, you will get into troubles. And also in electrical signal. Yeah.
I think we've lost your presentation.
Yeah.
Yeah.
Huh. Okay. Let me try to share the screen once again. And let me know if you can see it.
No, not yet. I don't know, for some reason I need to go back on stage to even speak.
That's interesting. I can try connecting from another computer, although I'll lose the camera, but...
What does it say? Is it giving you an error or something? Or?
Actually, it's showing the circle and, trying to load something and doesn't really complete it. I can try stopping the share and maybe the
that's
share
probably
again.
the thing that'll fix it.
Yeah, but it's still just turning the wheel.
Just kill the window maybe and start again, because it looks like it lost track of that window from a sharing.
Share the screen. I cannot click the share screen anymore. Okay, let me try rejoining the session. Sorry about. Okay, can you let me know whether you can see the slides now?
Yes.
And okay, so when did the slides broke?
Before this, go back one, I would say.
Before this, okay, so let's move back and try to see whether we can start from here. Okay, yeah, so let's hope everything works now. So as I was saying before, the frequency synchronization is called synchronization. So basically, we make sure that the frequency matches on all our devices, and events happen at the same rate. And if we are talking about the digital signals, we also want to make sure that the signals are sampled correctly. So in the case when the clock is synchronized with the data stream, then we will, and in this example, let's assume we are sampling the data on the raising edge of the clock. So in this case, when the frequencies matches, then we will sample the data correctly in all of the cases. And in case they are out of sync, then we will sample data correctly for some time, but then we can get samples from indefined states when the data transitions, or even completely miss some data in between the clock signals. So why do we actually want to synchronize frequency? The first thing is that we want the transmit side and receive side run at the same frequency. That's done in almost all Ethernet devices, or rather PHYs right now. So the receive side can tune its clock to match whatever it receives. Then the 2G, 3G, and 4G required for radio access networks, the devices there that uses the frequency division duplexing, which is basically the cell towers have the different bandwidth window for transmitting the data and receiving the data. So there are dedicated downstream and upstream windows. And obviously, if we get out of sync there, we will start scrambling the signal of the other cell tower that's in range. So we cannot really allow that. And also the backhaul needs to run at the same rate as our radio units or BTSs. So the second thing is the phase synchronization. And what that means is that the leading edges of our clock signal will happen at the same moments. And events in our system will start at the exact same point in time. And also this implies in most cases that the frequency will be synchronized as well, so the events will happen at the same rate. And why do we care? That's mainly because of the newer version of the LTE standard, which is the TDD, which stands for time division duplex. In this method, the receiver and transmitter has allocated time slots. And so there is a window when the base station talks to the phone and the window when the phone talks to the base station. So in that case, when you actually traverse and between the cell towers and don't want the call to be dropped, you need to have the phase of the signal, like, you need the cell towers to be in sync if it comes to the phase of the signal, and exactly phase of the second, so that the transmit and receive windows are the same between the cell towers. And when you actually traverse between them, you will hand over without a problem. And the 3GPP allocated actually the ±3 microsecond between two base stations in the small cell towers. So the cell towers cannot have the phase difference bigger than 3 microsecond per second. And actually, to allow for this one, if you put your grandmaster somewhere in the backhaul network, you need to make sure that every single cell tower is within the 1.5 microsecond limit from the grandmaster. And the last thing that we're going to talk about is the time of day synchronization. So the leading edges are at the identical moments, so they will start. So the phase will be synchronized, but additionally, each period is marked and dated, so we know which second is it, not only that the second starts. And they happen at the same rate. So why do we need this? Obviously for billing reasons, to maintain the quality of service, and to get logs across the network and synchronize events that happens in different parts of the network. So the standard, the G.8 standard defines two main types of timing signals. First one is physical layer timing signals. In this case, the leading edges of the physical clock are actually the significant instance. So whatever we try to synchronize to are the edges. And this signal is mainly prone to jitter and wander error. The jitter is a short-term error, and the wander is a long-term deviation of the frequency. And the other one is a packet-based timing signal. In this way, we send series of packets with significant instance. So there is, for example, in 1588, there is a preamble in each of the packets, which when is detected by the PHY, it is timestamped, and then this timestamp goes to the user. In this case, we need to make sure that we send those packets at some rates, and that we can recover the frequency from those packets. And obviously the main problems with packet timing signals is that there is a packet delay variation that's not really deterministic in our network and depends on some physical, maybe not physical, but properties of the network and usage of the network. So basically whenever the load of network is bigger, the packet delay variation will increase and so on. So how can we transmit the frequency? We can do it either using the physical layer distribution. So in that case, we connect the reference clock to our leading node, and then connect just the Ethernet port of our leader device to our Ethernet equipment clock, which is basically the other Sinki enabled device, and daisy chain them to the last part of the network where we can recover the clock, which will be basically tied to the reference clock that is on the other side. And if it comes to packet layer distribution, we connect the reference clock to the leader or a grandmaster, and then send the packets throughout the network and somehow try to match the frequency on the follower side to allow recovering it on the other side. So a short summary of this chapter. There are three aspects of synchronization, which are frequency, phase, and time. And frequency can be transmitted in different ways, either through packet layer, packet-based, or the physical layer. And more areas actually need synchronization, especially within the 5G and telco space. So I don't know if we want to do some questions after each chapters, or we want to move along and do the Q&A at the end of session. We will probably do the Q&A at the end of session. So let's move on to the next chapter, which is packet-based time and phase distribution. On the example of 1588 protocol. So how it happens is that we have our grandmaster or the leader side, and the first step to actually start with is the generation phase. So we first need to somehow synchronize our source of timestamps to the reference clock, for example, the GNSS receiver or the atomic clock or anything along those lines. And then we need to create packets that are actually carrying information about this physical source. Then we have the transmission part, the transfer part, where the packets are transmitted over packet network. And in the end, we have the follower side and the recovery stage, where we try to regenerate the physical frequency from the packets that we received from our network. In more details how it works, as I said before, there is a significant instant in every packet that we send, which is basically the moment where we capture the timestamp. And we carry additional information in the timed packets, such as the timestamp of when the packet was sent from the other side, or when it was, or any other information about the clock that was used as the source to generate those packets. And then we send the packets at a specified rate. And the important part is that, for example, for 1588, only the rate is actually specified. but there is no requirement for the packets to be sent at the same at the even spacing. So we can bunch couple of packets and then send others. For example, bunch couple packets in the end of the second and a bunch of the packets at the beginning, and we will still meet the requirement of 1588. They don't really need to be evenly spaced. So timing signals can be periodic in the circuit emulation service, which is not really very popular, or aperiodic in most of the cases like NTP or PTP. And along with the clock information, we can carry additional data. So we can, for example, carry the timestamps or the quality, as I said previously. So how it actually works, basically we start our reference clock. Let's assume this represents not single ticks of high frequency clock, but let's say the reference clock is the 1 PPS clock. So we start at our best knowledge how the clock should look like, and we wait for the packet to arrive. We see that our first packet from our stream arrived at a bit earlier than we thought the second will actually be. So we need to increase the frequency, and we do that for next couple of seconds and get the other packet. And so now we see that actually, we are running too fast. We need to go a bit slower. And so we tune our oscillator somehow to actually go a bit slower. And in the end, we can see that, okay, we actually matched what the other side sends us. So we are good, and now we are synchronized. And I will go very briefly through those slides that actually talks about how the 1588 works. So let's assume we have our leader side and our follower side, and they are out of sync. And let's assume that path delay is 1 second for easier math. So the first thing where the 1588 starts is that we will receive the sync packet from the leader, and the follower will capture the timestamp when this packet arrived. And after this, in the two-step version of 1588, we will get the follow-up packet, which will contain the timestamp when the sync packet actually left the leader side. So in this case, we will get the T2, which is the follower's side time, or when the sync packet was received, and we will get the T1 timestamp, which is when the packet was sent by the leader. And as a result, we can calculate the offset and apply it, so we can adjust the clock by those missing seconds. And now we will, obviously, some time will pass there. We don't yet know what the delay of the path is, so we can only compensate for the difference of the clocks. So we at this stage, the T3 will be at this value, and we will then send the delay request from the follower to the leader. The follower will capture the timestamp when this packet was sent to the leader, and the leader will capture the timestamp of when this packet was received on the leader side, and will send that information back to the follower using the delay response message. And as a result, we will get the round trip delay. And we will estimate that the delay of the path is actually half of the round trip. So now we have all the data. So we know that we have the delay of 1 second, and we know what our time is. So next time we receive the sync and follow-up message, we can compensate for the offset and for the path delay. And as a result, we will finally get in sync with the leader. Okay, so now let's move on to Sinki. So this is the physical layer frequency distribution. So what is Sinki? The Sinki is actually using Ethernet fabric to transmit the frequency over physical layer. Since in very traditional Ethernet was intended to actually transfer data asynchronously, so there were we weren't able to do Sinki on like 10 base T adapters because they were only transmitting data when there was something to do. But since the faster adapters like 100 megabits, the 1 gigabit, and all the others actually do not have the idle period, but they constantly fill them with pulses. So as a result, we can use those pulses to actually tune our frequency generator, our clock generator, to match the frequency that is on the other end. So as a result, we use the Ethernet fabric to transmit the frequency over physical layer. The other requirement of Sinki is to use high stability oscillators to generate line frequency. In the traditional Ethernet, the 802.1 standard requires every single oscillator in our Ethernet adapters to run at plus minus 100 ppm frequency, which means that we will receive the data from the other side. And like I said, there is a PLL in the receive side, so this part will be tuned to whatever was coming on the other side. But then we will actually transmit the data to another element using our own frequency, which can be off by, for example, 100 ppms. And in Sinki, there is a requirement that each of the reference clocks will actually have the plus minus 4.6 ppms. So there is a much stricter limit on the frequency offset from what we should have. And actually, this means that even on start with the Sinki adapters have some requirements that they need to build on top of. So in Sinki, every Ethernet equipment clock, which is basically our clock inside the adapter, logs itself to the incoming frequency that is recovered from the receive side. All the clocks are logged and traceable to the source of the signal. And when they are logged, they can achieve very, very high accuracy of plus minus 10 parts per trillion. And it has no impact to the packet layer, and it's guarded by couple standards, but I won't obviously read them. They're only for reference. So the Sinki has two main building blocks. The first one is the Ethernet PHY that is capable of recovering the recovered clock from the incoming packets on the receive side of the PHY. This recovered clock is then outputted to a physical pin of the PHY or the whole package, and then it's going to the second part of the Sinki capable adapter, which is the PLL, which is the phase lock loop device, and this is basically the kind of a clock generator that can slightly tune the frequency that it generates to actually match whatever it gets on the input. So the PLL of the device can either be tuned to the external reference clock or to the recovered clock that goes out of the PHY. And this PLL will generate the clock at which the Ethernet PHY will transmit the packets to the next device. And also, this PLL can be used to, for example, generate the recovered clock that can be used by other devices like radio units or other similar devices. Okay, so the next important thing in Sinki is that the DPLL itself can have different states. So when it starts, it will start as free running clock. So the system clock that is generated by the DPLL, which is the one that is going there back to the PHY or to the whole package. So this system clock will run independently. We haven't have any reference to tune to, or we passed the holdover time. In this case, the clock generator will run independently of another sources. So basically, this system clock will be the representation of as good as we can get with our oscillator. The next state is when we lock, so we will get the reference clock and we will start tracking it. And once this clock is valid, we will synchronize our frequency to the frequency of that incoming reference clock. And basically, the clock that we are generating will be tightly synchronized. Its frequency will be tightly coupled to whatever we get at the input. And the third state is holdover. So whenever we lose the reference clock for a relatively short period of time, we will enter the holdover state. And in this state, we will still generate the output signal, which will be as good as we can get with our oscillator, but it will still be close to the reference clock if it's gone for a short period of time. And whenever the reference clock is then going back, we will go back to tracking the reference clock. So basically, it's a state when we were synchronized to a valid reference, but now we aren't for a short period. And the fourth, which is maybe not a state, but possibility, is to automatically track different clocks and switch between them. So in this case, when we have our reference clock number one going away at a certain period of time, at the certain point in time, but the other clock is still running, we will switch to tracking the other clock, still track it, and whenever the higher priority clock will get back, we will start tracking back the reference clock number one. Okay, so now how can we actually determine the reference clock in our system? Sorry. So let's assume we have a primary reference clock, which is the ultimate source of clock in the systems, connected to this network equipment node. And then we have a synchronization supply unit A, which is a bit lower than primary reference, but it's still a very good clock connected to the to the network equipment at the bottom. And then we connect one port of this network equipment to the one that is connected to the primary reference, and this one to the one that is connected to the supply unit. And then there is a question, which reference should this element use? So there are two solutions to that. The first one is that we have a QL disabled, so we are not transmitting the quality level of the signal across the network. And in this case, we use fixed provisioning configurations. So we basically either force a reference and then track for the signal failure. So we will log to, for example, to the network element that's at the top. But when this link is broken, we will stop tracking it and enter holdover. Or there is a local priority mode. So whenever this, we can set up that we will at the first time, like with the higher priority, we will use this connection. And if it's gone, we will use this. And then this network element will automatically switch whenever this link is broken. The main issue of QL disabled mode is that the QL disabled mode will only track the link between the network elements, but is unable to track whenever the source, the primary reference source connection to the network equipment is actually still there. So if this path is broken, this element will not know what happened. That's why we can go back to that same question, but now add some kind of QL enabled mode, which will actually transmit the quality levels of what clock do we have. So the element at the top will transmit the QL PRC, and the element at the bottom will transmit the QL SSU information, and this network element will then be able to automatically assign the priority to each of the ports that it has, and then transmit the QL PRC whenever it's active to the next element. So in this case, we have a dynamic configuration. We can still force the reference, but if the reference is not forced, then this automatic process will be used. And obviously, we will still track for the signal failure. And in this mode, we will be able to detect whether this connection is gone, because the network element that's connected to our primary reference clock will start broadcasting the messages that you should not use me as the reference because I lost track of my reference. Okay, now a couple words about traceability. So there are a couple methods of tracing the frequency source. They are obviously depending on which method you are using. So in case of physical layer distribution, in case of Sinki, the standard way to trace the frequency sources is to use the ESMC messages between the nodes. So every node will send the information about what clock does it see, and the best one will be chosen to actually be a source of frequency for the whole network. And if it comes to packet-based distribution, in the PTP protocol, there is an announce message that needs to be sent by our leader side. And this message contains the field that's named PTP clock class, which is basically the quality level of how good the leader side is, whether it's a grandmaster or any other leader. So what is the ESMC that's actually used for tracking the quality in the Sinki? So this is the Ethernet synchronization messaging channel. It's based on slow protocols and transmit the synchronization status messages, which contains the quality levels. And there are two main types of messages, which one is the heartbeat, which is sent every second. Whenever we don't receive the heartbeat for more than 5 seconds, we transit into the failed state. And there are event messages that are sent when there is something going on. For example, when we lose track of our external source of the frequency, we need to send the event message that tells the other side that we lost track of it. And data is mapped into TLVs. Here's how those packets look like. I won't really go over too many details of it. It's more for a reference. But basically, it contains TLVs fields, which basically have the SSM codes, which relates to the quality levels of our source. And how those ESMC messages and QLs work. So in this case, like we said previously, every Ethernet equipment clock or network element that has a higher clock class than the other side will send us our clock class. And if this element receives the PRC on this port, it needs to send back the do not use message to prevent loops. So this traverses throughout the network, and basically all the equipment or all our Ethernet equipment clocks will be then synchronized to the primary reference that's driving this node. And the quality level will be basically used then. So when the failure happens, and for example, we break the link here, what happens? There we enter the transient mode. So our Ethernet equipment clock that's in here will say that all I have is the QLEEC, which is the basic quality. And as we see, this one has the connection to the supply unit. So this one will have a higher clock class than the EEC, and it will send back the information that okay, I have the SSUA quality level. So in this case, this clock will actually tune its own oscillator to the frequency coming from the SSU, and pass along the information to the other element that now I am tuned to the SSU clock. And since all this one had was the QLEEC, it will send do not use me because I by default have a lower clock class. And in the stable mode, this EEC will also send do not use to this one. So that all the network will be driven by the SSU that's connected to the element at the bottom. So now a short recap. Sinki transfers frequency over physical layer, which means we are using the physical clock that's on the line. It doesn't rely on any packets and doesn't interrupt any packet transmission. It can work either in the QL enabled or QL disabled mode. And if it works in the QL enabled mode, it will use ESMC messages to trace clock class and trace events. And now a short summary and a comparison of both PTP and Sinki, and also a GPS, which is the primary source of frequency and time in most systems. All of them can synchronize the frequency. Only GPS and PTP, well, GPS configured to output 1 PPS signal, and PTP can synchronize the phase. and the same with the time of day. If it comes to the frequency accuracy, GPS is the ultimate source in our networks. If it comes to PTP, it is challenged by the packet deviation, so the frequency accuracy is lower than GPS. It's still pretty good, but it's not as good as GPS. And since Sinki works on the physical layer signals, it can still maintain very high frequency accuracy. If it comes to time and phase accuracy, the GPS provides obviously very high accuracy because it can output 1 pulse per second signals. So it will send 1 PPS signal and the time of day message on the different channel. So this is the highest reference. Then PTP is also can also have very high quality, up to couple nanoseconds, and Sinki does not transfer this. If it comes to the holdover, in default configuration, GPS receivers will stop giving the 1 PPS once they lose traceability of the satellites, and PTP and Sinki can still run and will enter the holdover mode if they don't see the incoming signal for quite some time. And the connection to the GPS is usually done by the RF signals, so the physical 1 PPS signal and for example, the RS for the time of day information. And both PTP and Sinki runs on Ethernet. So the frequency, main ways of transferring the frequency over our networks are either physical layer, which is Sinki, or the packet-based using 1588. The quality of source of frequency can be traced back to the source. And for the best results, it's best to use 1588 for phase and time of day, and then use Sinki to actually synchronize the frequency. And the 1588 is prone to packet delay variation and delay asymmetry. Okay, so do we want to have a short discussion about the theory part before we move on to Linux interfaces, or? Rupa, you're on mute.
Oh, sorry.
Okay.
Shrijit was saying something too. Maybe.
I can't hear him.
Yeah, we can't hear him. I see one question on chat. PJ, you see the question?
Yeah, how can skew between ref clock 1 and 2 be handled? So this is the question to the slide. To the slide that was showing reference clocks. Basically, in this case, we have some guardrails that tells us whether the signal that we see on each of the references is a valid or expected one or not. So whenever the reference clock number 1 will meet the criteria, so it will not be, for example, further away than couple ppbs, then what we think of as the correct frequency, then we will still track reference clock 1, and if it leaves the window, so it suddenly shows a different frequency, we will then switch over to the backup or to the holdover, depending whether we have the reference clock 2 or not.
Cool, thanks, Maciej. PJ, does that answer your question? I mean, if anybody else has a question, we can get you back on stage as well.
Yes, I just wanted to say, if you have a question and you want to ask it, do one thing, either put it in the chat or raise your hand, and Rupa or I will move you so you'll get a chance to speak and be seen.
Feel free to post your questions on chat too.
Yep.
Okay. So since I'm not seeing any raised hands, I have a question, Maciej. So for
Okay.
so why is so you said the Sinki scheme cannot actually provide phase information. Is that
Yes.
a design
Sinki.
choice? I mean, it
Well,
should be more
Sinki
accurate,
by
right?
Well, yeah, but Sinki does not transfer the phase of the signal. Like you cannot extract the 1 pulse per second from the higher frequency signal unless you add some special information. And since signal is working on the Sinki, is working on the regular Ethernet, it cannot really add the information about the phase. So as a result, you can use it as the source of the frequency. So you can, for example, divide it by something, get it out to the DPLL, tune your DPLL, and then your frequency will match whatever was seen on the receiver side. But you cannot get the phase, for example, know when the 1 second starts. That's where you need the PTP or external signals.
I guess I mean, you could have done it with some kind of pulse signaling, right? It wouldn't have been impossible to do. I guess my question was,
Yeah.
it sounds like it was a design choice to not go down that road and leave it to PTP. Is that?
Yes, that is the design choice because we want to have a compatibility with regular Ethernet, which could be confused. But when you see some strange pulses.
I see. So I see. Because this is always on, you don't want to have a one-side problem. Got it.
Yeah.
Got it.
Okay, so I see that PJ asked, do we assume that reference clock 1 and the backup clock are in sync? Not always. Generally, we would like to assume that all of them are somehow related, like, how to say it? They shouldn't. Well, okay, the DPLL in the principle can tune to any frequency. So the way it works, you set up the expected input frequency, and then the DPLL will tune the frequency that it generates to be like derivative of what it sees at the input. So there are some guardrails built into the telco standards that says that, for example, your input signal cannot be further away in frequency than couple ppbs. So you can use different frequency of the signals, so they don't need to be in sync, but they still need to meet some criteria. So for example, you can have at one input, you can sync to the 1 PPS signal, and on the other input, you can sync to the 10 megahertz used as the frequency reference, which is commonly used in telco systems. And in that case, you can, when you lose the 10 meg signal, for example, you will switch back to 1 PPS or the other way around. So they don't need to be in sync, and they need to be in sync. They can run at different rates, but they should be in sync. Okay. So if there are no other questions, we can move on to what's currently in Linux and what are the proposed solutions to that.
Sounds good.
Okay, so let's move on to Linux kernel interfaces for Sinki, which is a pretty short slide because there are none of them. If you grab kernel for Sinki or ESMC or QLs, you won't really find too much because those interfaces aren't there. And okay, so like I said, Sinki has two main building blocks, which one is the PHY and the other is the DPLL or the PLL. So what are the basic building blocks? The first one that we need is the 5-clock redirection configuration, and the other one is the clock generator state monitoring. So we need the interface to say which port is our source connected to, and which one should we recover the clock from. And we need to monitor the state of our PLL to say whether this clock is okay or not, and if we are using external clocks, whether they are good or not. And the third interface that is a bit more optional is the interface to configure the clock generator, configure its more advanced features. So if it comes to the 5-clock redirection, the scope is per physical port. It needs to support multiple output pins and needs to somehow map the physical ports to those pins. And this interface will be a simple one. It will only allow user to enable or disable clock on a given pin. And also optionally may read the clock frequency, so that if we want to manually configure the PLL, we can read what the PLL should expect on those pins. And if it comes to the clock generator state monitoring, the scope is per device. The whole Ethernet adapter usually has a single PLL. So the whole NIC will run on a single clock generator. So the scope will be per device. And it needs to return the state of the clock generator, like I listed previously. So it will need to tell you whether you are locked to any of the reference signals, or you lost it and you entered holdover, or anything else incorrect happens. And the other interface that we need to have is the one that will asynchronously return us the events when the clock generator state changes. So whenever we suddenly drop the signal, we will get the event that the clock generator entered holdover. And the clock generator configuration interface will also be per device, and it will be used for advanced clock generator configurations, such as changing the priority of the pins that it has, or expected frequency on those pins, or any additional features like phase delays, or I don't know, any other special source that the PLL manufacturer put into it. So now the couple considerations about the interfaces that we have available in the kernel. We have good old IOCTLs, and those are actually standard in the Linux PTP stack. So this is pretty important to actually maintain them, to not have to add all other interfaces into the whole Linux PTP project. The other interface is the sysfs, which is currently a standard for PTP clock. For example, the PTP pins are configured using the sysfs under sysclass PTP and the PTP device pins. So this is also a standard interface for a bit more advanced configuration. And we have a devlink, which is very good for configuring all the advanced features. So it's good because it's expandable, and we can add parser-like commands to it, which are more human-friendly and will be easier to support more advanced features using this one. but is unfortunately not supported by the Linux PTP stack. So the proposed interfaces mapping, the proposal that we have is to use the IOCTL and define a new IOCTL operation and sysfs file per port, so that we can use whatever is actually in the Linux PTP project to enable file redirection. For the clock generator state monitoring, it's probably best to create a sysfs file and the event queue in the PTP clock device. So that will be extension to the PTP subsystem. And if it comes to the clock generation configuration, which is the advanced interface, we suggest to use the devlink parameters so that we can allow multiple vendors to actually customize this interface to what they need it to be, because different DPLLs have completely different parameters to change. Yeah, and that sums up this presentation. We hope to submit the RFC soon, but we still are working on it. So yeah, let's now open the discussion.
Thanks, Maciej. Anybody questions? Hang on, there is. Okay, Shujit is asking a question. Which devices support Sinki? Are any available on the market?
Well, I think that Silicom sells some of the Sinki enabled adapters, but there are some of them. Definitely, there are switches that supports it. I think Cisco is one of the manufacturers that supports Sinki in their telco-oriented switches. So yes, there are switches and there are some network adapters that support Sinki right now.
Any Intel ones? I can't say for sure any NVIDIA ones.
Not yet. We just announced one of them, but it's not yet available.
Same with NVIDIA as far as I know. People want to raise hands? So the kernel interfaces, sorry, I've been going back and forth, so I missed that, but you are working on extending that for Sinki?
Yes, we are actually working on extending the existing interfaces, and one of the challenges is that usually we don't add new IOCTLs, so that's the ask here, to actually allow one additional IOCTL to enable clocks, simply because the Linux PTP stack does not have the support for netlink or devlink interfaces.
Yeah.
And the fastest way, since that's actually the only operation that's crucial, it would be easiest to simply add the IOCTL that will enable this per port.
Makes sense. It does have some netlink, but it's all for the topology discovery, right? Interfaces and so on.
Yeah. It was a very, very simple implementation, as far as I remember, very targeted. So it does not have enough to actually allow easy implementation of something new.
I think Marvel is saying on chat that they do have switching ASICs that support Sinki.
Yeah, I know there are more of them. I just remember that out of top of my head that, for example, Cisco have it, but I'm sure there are much more devices. Like there are definitely Marvel PHYs that support Sinki. Yeah.
I don't see any other questions.
Okay, so we should probably wrap up.
Cool. Thanks a lot, Maciej. This was great.
Okay, thanks a lot for attending this session and have a great rest of the conference.
Yeah, you have a lot of emojis.
Yeah, I see it. Thank you.
Cool. Thanks a lot. Thanks, everyone.
Thanks. Bye.